Okay, so let's get started. So a couple of reminders. Homework 5 is due tonight. Okay, so if you haven't finished your homework 5, make sure you finish them by midnight. Homework 6 is due on Tuesday next week. Okay, and then we'll have exam in the following week. For in-seat classroom, the disinfection, KDM medicine. Okay, all right. So today we'll be looking at start to look at the chapter 6, uniform circular motion and gravitation. Okay, so I think we have pretty much been focusing on linear motion. All right, now there's another kind of motion of object that is very common in the universe. So if you look at our solar system, you can see all the planets are going in the circular motion. Okay, and then also maybe on atomic scale, if you look deep into the one particular atom, you'll see that electrons are orbiting also around the nucleus. Okay, so that's a very common type of motion for an object. So we'll be looking at this one here in this chapter. Um, so to start with, we kind of will have like analog or comparison of the linear motion and circular motion. Okay, so in linear motion, the first thing quantity we look at was the position. So here we can also look at the position for circular motion, but in this case, we will be using the angular as the or angular position as the analog of the linear position. Okay, so because the object is going in a circle, right? So then you can pretty much relate its position with the angle reference to a reference line. Okay, so this is the analog to an origin for linear motion. Okay, so you take a line for your reference line, then you can measure the angle between that reference line and then where the position of the object starting from the center of the circle there. Okay, so that's the angular position theta. All right. Um, so I think when we use angles, most often you will use degrees as the unit, right? But actually for angle, the SI unit is in radians, okay? So that is like 2 pi, that is in radians, that's equivalent to 360 degrees, okay? So that's the conversion between radian and degrees. So 2 pi is equal to 360 degrees, all right? And for radian, okay, so when you do calculation or when you put into an equation, you can also treat it as dimensionless, okay? So if someone tells you angle is equal to 3 without a unit, then it's probably meant to be 3 in radians, okay, instead of in degrees. All right. Also, you can measure the angle um, in this direction, right? You can also measure the angle in the opposite direction, right? So this is this direction here, counterclockwise. That's the convention people usually take to be the positive direction, all right? And then if you measure it clockwise direction, then that's negative direction, okay? It's just like for a position, you have positive direction and negative direction, okay? So in this case, counterclockwise is the positive direction, clockwise is negative direction, okay? So that's the convention there. And then, as I mentioned, um, if you have 360 degrees, okay, so that means you are um, moving by one full revolution, okay? So in certain cases, you'll see also the angular position expressed in the unit of revolutions, or ReV stands for revolutions, okay? So if it's one revolution, that means it's 360 in degrees, also 2 pi in radians, okay? So that's another unit you might be seeing. All right. Now, if you have a particular point, say in this case, again, on this wheel here, it moved by the angle theta, right? Now, physically, it moves by the length here. So you can like take the measurement of the length over here. So this is called arc length, okay? So this is in dimension of length here. So arc length here is equal to the radius times the angular position or angular displacement over there, okay? So when you are using this equation, relate arc length to the angle or angular position, then the angular position should be in the SI unit. Okay, so when you use the equation, you want to use the SI unit. Okay, so then this arc length should be will be in meters, radius should be in meters, and then the angle in radians, that means dimensionless. So then length equal to length, okay, times dimensionless, which is also the length there. Okay. All right. So that's angular position. The second quantity here we will be looking at is the angular velocity. Okay. So then similar to linear velocity, when we define linear velocity, we take the difference in the position divided by the time t. So here we will again take the difference in the position, which is the angular position, and divide by the time t. Okay, delta t time interval. So in that case, you will have your angular velocity. Okay, so this is looks like a W, but it's omega. Okay, so it's omega average equal to delta theta divided by delta t. Okay, so then this should be in radians. The SI unit should be radians per second or just per second because radian is dimensionless. Okay, all right. So when you do that equation over there, delta theta, that means you'll be doing theta final minus theta initial if the point travels from here to here, okay? And then that gives you delta theta. Also on the reference line, I just want to comment out that this can be arbitrary again, okay? So you can take this reference line anywhere. You can say this is the starting your reference line. That's fine. Okay. So just as when we define the origin of a coordinate system, it can be arbitrary. Okay. So this it can be also arbitrary. All right. So you can calculate the average angular velocity by doing change in angular position over change in time t. Now, if you take the limit of delta t equal to 0, all right, that means you are looking at particular instance, then you'll be looking at your instantaneous angular velocity. Okay, so that's taking the min limit when delta t goes to 0. Okay, all right. And then it's a velocity, so it should be having the same SI unit for the average velocity, radians per second or just per second or second inverse. Okay. All right. So let's take a look at a practice problem here on this guy here. It says express your angular velocity of the second hand on a clock in the following units. Okay, so this is pretty much just practicing the unit conversion between revolution degree and radians. Okay, and then also like hours, minute, and second. Okay, so think about what would be the angular velocity of the second hand. Okay, so you can consider like when it goes through a full revolution. So then change in position is 2 pi, okay, in radians or 1 revolution. And then the time it takes for the second hand to go 1 full revolution, it should be 60 seconds, right? So you can get the angular velocity by looking at that, right? You can submit your responses by clicking on this. And it should get you here. All right. So let's take a look here together, okay? So the first one is asking you what's the angular velocity in revolution per hour, okay? So then you can imagine here for the second arm, if it goes one full revolution, then that's 60 minutes, right? Or 60 seconds or 1 minute, right? So then omega here for the second will be delta theta over delta t. So in one revolution, it's 60 seconds. So then it's one revolution over 60 seconds, right? But you want to have this in revolution per hour. So you can convert the second to hours. Okay, so in 1 hour, there's 3,600 second there. Okay, so then that tells you 60 over divide by 60. This one gives you 60 here. Second goes away. So that's 60 revolutions per hour. Okay, so that's A. For B, it says in expressed in degrees per minute. Okay, so omega is equal to, again, you can use that one revolution per 60 second, right? So now convert revolution into degrees. You put revolution down here. In one revolution, that's 360 degrees. Okay, and then second down here, you put second up there per minute, right? So minute down here. So in 1 minute, that's 60 seconds. Okay, so then that will give you 360 degrees per minute. Okay, that's in degrees per minute. That's put DEG instead of a circle there. DEG here. Okay. All right. The third one here is ask you in radians per second. Okay. So radians per second, again, you can start with this guy here, one revolution per 60 seconds. All right. So then just convert revolutions into radians. Radians on top, 2 pi in radians in one revolution. Okay. So then this will give you 2 pi over 60, which is 0.150 radians per second. Okay, so that's pretty much just unit conversion over here. All right, now to extend this problem, you can also check on the minute hand. All right, so what's its angular velocity? You can also look at the hour hand. What's the angular velocity? Okay, so for minute hand, if it goes one full revolution, then the time it takes for the minute hand will be 1 hour. Okay, For the hour hand, if it goes through one full revolution, time takes will be 12 hours. Okay, so you can start from there and then calculate your angular velocities for those 3 arms. Okay. All right, let me take a quick look on what you guys submit here. So the first one, 60. Yep. Second one, 360. Okay. The last one, not quite right there. All right. Yeah. So compare what you have with the solution. Okay, you see where it went wrong. Okay. Any questions you guys might have? Okay. All right. So, all right. All right. So we are going to move on here. So, so we have talked about angular displacement and then angular velocity. Okay, so let's see how you can relate angular position, angular displacement to the linear displacement. Okay, so delta theta is the angular displacement. All right, let's change in angular position, and then the arc length over here, that is the distance travel. Okay, you can measure the length of that, so that's referring to linear displacement. Okay, so the relationship between the two, as I mentioned, or as we checked earlier, was the delta s should be equal to r times delta theta, right? So then delta theta should be equal to delta s over r. Okay, so it's the arc length divided by the radius will give you the angular displacement, and then again the angular displacement should be in the unit of radians. Okay, we should be keeping the SI units in the equation here. Or you can think about if the displacement in angular displacement go one full revolution, then the arc length should be 2 pi times r would be the circumference of the circle, right? Then the delta theta should be equal to 2 pi, right? So in that scenario, you can also see that delta theta is going to be equal to the arc length divided by r. Okay, so that's the linear relation or the relationship of linear and angular displacement. So pretty much you will have linear quantity divided by r that gives you the angular quantity. Okay, so if you are at different locations here with respect to the center, okay, if you are at R1 here and then R2 here, although you might be going through the same angular displacement, but your linear displacement or arc length travel, they are different, okay? So they are proportional to the radius you have, okay? So just keeping that in mind. All right. So the next we are going to check on the relationship of linear and angular speed of the velocity. Okay. So when we do the angular speed or the angular velocity, we do theta divided by t, right? And theta from the previous couple of slides back, we know that angular displacement is equal to the arc length or the linear displacement divided by r. So then you can replace the theta here with this guy, okay? So it becomes this here. So then omega angular velocity is equal to delta s over r. Okay, now this guy is in the denominator here. You can drop it down here, all right? And when you do change in arc length over t, so that's the linear displacement over t, right? That will give you linear velocity, v, right? Then you have the r there. So then angular velocity is equal to linear velocity divided by r. Okay, so very similar to the angular displacement, which is equal to the linear displacement divided by r. Okay, so pretty much the same relationship over here. So angular velocity equal to linear velocity divided by r. Okay, or the other way around, you can put the linear velocity equal to r times angular velocity. Okay. All right. So we have checked on the displacement, we have checked on the velocities, and now we are going to take a look on the oscillation, okay? So for the angular oscillation, in this case, we will call it centripetal oscillation because the direction of the oscillation here is always pointing towards the center, okay? So you can see that by thinking about if the angle, change in angle is very small, right? If this is very small, then change in velocity here, over there, you can kind of move these two vectors parallel over. So it's kind of zooming for the vector, velocity vectors here. So you can see this delta V. If the angle is very small, then this guy, this angle is very small. Okay, you can approach that to be 0. So you can see the change in velocity should be pretty much perpendicular to the velocity. All right. So if that's perpendicular to the velocity, that means it's pointing towards the center. Okay. So changing in velocity is pointing towards the center. That means it's pointing the oscillation is also pointing towards the center because the oscillation should have the same direction as the change in velocity, right? Because oscillation equal to change in velocity divided by time t. All right. So the direction should be always going towards the center. All right. So that's why it gets the name of in centripetal oscillation. All right. So we can look at the relationship here. Let me see if I have. Okay. Yes. All right. But let me just first comment on the this red triangle over here, and then this green triangle over here, okay? So in these two triangles, you have this, two sides are the same here. So this is R, this is R, okay? And then on this triangle, you have V1 and V2 equal to each other. Assuming this is a uniform circular motion, that means the velocity doesn't change, okay? Or the magnitude of velocity doesn't change, the speed doesn't change. So then V1 and then V2 should have the same length, okay? And also, if this angle is theta theta, then this should be theta theta, right? Because this guy is perpendicular to this guy is perpendicular to this, okay? So then when you move this guy over there, this angle should be the same as the angle, or this angle should be the same as that angle, okay? So for two triangles, if they have the same angles here and here, and then if this side is equal to that side, and then also that side is equal to that side, so they are similar triangles, right? They have the same angles, all right? So for similar triangles, you can write the relationship of this delta V over this V1 or V2 because they are the same. That should be equal to delta R over R, okay? So, and then when the angle is very small, if you take the approximation of angle is very small, then this delta S is going to be approximately equal to this delta R, okay? So just keep that in mind. That's what we are going to use in the next equation over here. So as I mentioned, delta V over V is going to be equal to delta R over R. And then delta S is about the same as delta R. So you can replace delta R with delta S, okay? So now, given that oscillation is equal to delta V over delta T, then you can divide this equation, both sides of the equation by delta T, okay? So let me see. Maybe better write on the paper here. I think a couple of steps missing there. All right. Okay, so I'm going to just write down those two equations here. So delta V over V equals to delta R or delta S over R, right? So if you divide both sides by delta T, then you divide both sides by delta T here divided by delta T there, okay? Now what I need to do is I can move this guy to the other side, or I can multiply both sides by V, okay? So I can get rid of V here, all right? then delta V over delta T, that will give me oscillation, right? Because that's the definition for oscillation. It's equal to delta V over delta T. On the other side over here, okay, so then I have V here. I have delta S over delta T. That's the arc length over delta T. So linear displacement over delta T. So if you remember, if you do linear displacement over delta T, that gives you velocity or the speed, okay? So then you have a speed here. This is equal to the speed. So you have speed multiplied by speed over r. So then that gives you v squared over r, okay? So this is the magnitude for centripetal oscillation. It should be equal to the linear speed square over r, all right? Now earlier we saw that for linear speed is equal to r times omega. So then if you replace the v with r times omega, then centripetal oscillation is also equal to r squared omega squared divided by r, okay? Which will give you r times omega squared, okay? So your centripetal acceleration can be expressed in this form, and then it can also express in this form, okay? Depends on if you are given the angular speed or the linear speed, okay? So I think that's what we have on the slide. Before I change, let me put the camera over the slide, roughly. All right, so that's how these two expressions are derived. So your centripetal oscillation has a magnitude of v squared over r, or r times omega squared. Okay, so again, these two expression gives you the magnitude. Okay, and then the direction of the oscillation should be always pointing towards the center of the circle. Okay, indicated by the name. All right. So when we have, as we have the displacement, velocity, and oscillation for the circular motion, now we are going to apply Newton's second law, okay, just like what we learned before for the other type of the motion. All right. So the second law also applies here. If you have centripetal oscillation, then the force is equal to mass times the centripetal oscillation, okay? And then because this is centripetal oscillation, so then you should have centripetal force, okay? Because the force and then oscillation, they should have the same direction. Force is equal to mass, the scalar times a vector. So then those two should share the same direction. That's why the force is also called centripetal oscillation, centripetal force, okay? And again, the magnitude, because AC can be equal to V squared over R, or it can be equal to R times omega squared. So either way, so centripetal oscillation is equal to mv squared over R, or mr times omega squared, okay? Depends on if you know the linear velocity or the angular velocity, okay? All right. Okay, so we are going to take a look on this example here. So this one says the humpback whales sometimes catch fish by swimming rapidly in a circle, blowing a curtain of bubbles that confuses a school of fish and traps it in a small area where the whales can easily catch and eat them. Suppose a whale has a 28,000 kilogram mass and then swimming at 2.2 meters per second in a circle of 8.5 meters. What centripetal force must the whale generate? Okay, so it tells you mass, it tells you the speed, which is linear speed. Okay, by looking at the unit, you can tell it's a linear speed, it's in meters per second, and then it tells you the radius of r. Okay, so you should be able to calculate the centripetal force of this. Okay. All right, so I think on this one, it's quite straightforward. So for centripetal force, you are going to either use mv squared over r or the mr omega square. Because we are given m, we are given v, we are given r, so then we will just take this equation, not that one, right? So then you simply plug in the numbers. So 28 kilogram times the 2.2 meters per second square over 8.5 meters. Okay, so this should give you 1.6 roughly times 10 to the fourth newtons. Okay, so if you keep everything in SI unit, then the final answer should automatically in SI unit. Okay, in newtons. Okay. Questions? All right. So next we are going to look at some application of the centripetal force. Okay, so when you are driving your car, if you are making a turn, all right, then at that moment, at that time instant, okay, so you are on the part of the circular motion. Okay, if you look at bigger picture here, when you are turning, at the instant you are actually having a circular motion. Okay, because it's on a curvature there. So what happens is here is, if you look at the free body diagram of your car, there will be normal force, there will be weight, okay, and then there will be friction force on the tires to the sideways, okay. So and then if you look carefully, it says mu sub s, so that means static friction, okay. So for the tires, when the tire is rolling on the floor, okay, at the moment, actually that is static friction, okay. So if you look at the contact there, there's no relative motion on the tire at that moment, okay. So that should be referring to the static friction, all right. But in that case, the static friction is in the sideways, so then that's pointing towards the center of the circle, okay, of the curvature. So at that moment, the friction force is your centripetal force to provide the circular motion of the car at that instant, okay? Also, if when you are driving the car, if there's a dip on the road, okay, so then at that moment, you can see the curvature here, all right, for the road, that's part of the bigger circular motion, although the car is briefly just at that part of curvature for maybe a few seconds. But when it's traveling on a curved road surface there, then it's actually having circular motion, all right? In that case, the weight and then normal force, so because this is a circular motion, so you can see there should be a centripetal force pointing towards the center of the circle, okay? So then there should be a net force here. So M should be greater than the weight, okay? So in that sense, so if you feel it, if you are sitting on the car, when the car goes downhill, you'll feel like, or at the bottom of the curve here, you will feel like your apparent weight goes up, right? So that's because the normal force goes up, okay? Due to the circular motion there, all right? Okay, and then so in most of cases, or in many cases, when you are going on the ramp that is connecting the local roads to the highway, so you may realize that most of those ramps are banked at certain angle. Okay, that's because if the road surface is bent at certain angle, then you look at the free body diagram here for the weight here and then the normal force there. Okay, so in case that there's no friction force on the tires, then the normal force, the horizontal component of it, okay, will be the centripetal force. Now the vertical component of it will cancel out the weight, okay. Then the horizontal component of it will be the centripetal force that you need for the circular motion, because most of the ramps are curved, okay. It's in a circle or part of the curvature there. So then it's actually, when you are driving the car up the ramp, it's actually having a circular motion at that moment, and you would need the centripetal force there, okay? So to have the road surface banked at a certain angle, that helps you generate the centripetal force you need for the circular motion there, okay? All right, now let's take a look on this example here when it says if a car goes around a curve on the road that is banked at an angle of 21.5 degrees. So this angle, banked angle is 21.5 degrees. Now it says even though the road is slick, the car will stay on the road without any friction between its tires and the road when its speed is 19.8 meters per second. So it happens when if it's raining or if the road is icy, okay, so then that bank angle will help, okay, hold the car on the road, not getting off the road there, okay? So it's asking what's the radius of the curvature, okay? So it tells you that if the car travels at that speed, then it doesn't need the friction force, all right? So then you'll just look at the weight of the car and then the normal force on the car, okay? Again, the vertical direction or the vertical component of normal force will cancel out the weight, okay? And then the horizontal component of the normal force should be your centripetal force, okay? So try to see if you can figure out this radius, okay? And then we can take a look on the solution together. So you want to write out the, or you want to check on the free body diagram, write out the net force in X direction and Y direction, all right? And then also apply Newton's second law to the circular motion here, all right? So then pretty much it's the X net force in the X direction, all right? Should be equal to the horizontal component of the normal force M, all right? And then the net force in Y direction should be equal to 0 because the normal direction, normal component of N should cancel out the weight, okay? So set those two up, you should be able to figure out the normal force, all right? And then take the normal force horizontal direction, that should be equal to the centripetal force to figure out the radius, okay? Because the radius should be in the centripetal force equation there. All right. So let's take a look here together. Okay, so this is the free body diagram. It says if there's no friction present, then we only look at the weight and normal force. Okay, so as you can see here, you can resolve the normal force into the vertical component and then the horizontal component. Okay, so this is the horizontal component should be n times sine of theta. Okay, and then for the vertical component over here, because this is theta, so then this is n cosine theta. Okay, so when you have done that, you can cross out the original normal force. Okay, so then you are looking at the normal force x component, y component, and then this weight. Okay, so then from the free body diagram here, you can tell for the x direction, it will be just the n cosine or n sine theta. All right, and then for the y component, it should be just n cosine theta minus mg. All right. Now from Newton's second law here, in the horizontal direction, the car is having the circular motion. Okay, so then the net force should be equal to the centripetal force. All right, which is mv squared over r. In the vertical direction, the car doesn't have motion in the vertical direction, so then acceleration should be 0. That means net force should be equal to 0. Okay. So then you can set that this guy equal to this guy, and then this guy equals to 0, right? So you can set up two equations, m sine of theta equals to mv squared over r, and then n cosine theta minus mg equals to 0, all right? So you'll get two equations here. And you actually have more than two unknowns here, okay? You have m as unknown, you have n as unknown, you have also r as unknown. Okay, so you actually have three unknowns here with two equations. Okay, the first look, by looking at it first, it seems like it's not possible to calculate for all the three unknowns, right? But we can take a closer look here. Okay, so starting from this guy here, we can actually relate n as mg. Okay, so in here, you can tell that n cosine theta is equal to mg, right? So then n is equal to mg over cosine theta, right? So after that, you can plug this expression into the n here. So then it tells you mg over cosine theta, okay, so this is m, times cosine theta is equal to mv squared over r, right? So then look at this relationship here, you probably figure out that the mass can cancel out, right? So then you have g sine over cosine, that means g of tangent of theta equals to v squared over r, right? So this is what you have for the expression over here. Now you can see r is the only unknown in this here, v is given, g is the 9.8, theta is the 21.5. So you should be able to solve for r here, okay? So multiply both sides by r, you'll cancel out the r on this side. So then r will be on this side, okay? Then further divide both sides by g tangent of theta, g tangent of theta to get rid of g tangent of theta there, okay? So then r is equal to v squared over g tangent of theta, okay? So v is 19.8 square divided by 9.8 meters per second square, tangent of 21.5 degrees, okay? So that will give you your radius. So it's about 101.6 meters or 102 meters. All right. So in this example, you can see probably you can see now the benefit of deriving the equation for the unknown, that you are looking for first. Okay, you can see that you will get rid of the m here. Okay, so you don't need m, because otherwise by looking at these two, you probably just say 3 unknowns with 2 equation unsolvable, right? But actually you can do it. Okay, so that's a benefit of writing the expression for the final quantity you are looking for here. Now you probably realize when you are when you see a speed limit sign, it doesn't specify the weight of your car, right? So that's because you can see here the m will cancel out, so the mass doesn't matter or the weight doesn't matter. Okay, even if you're a smaller car and a larger car, if it's the same curvature, they should keep the same speed limit. Okay, for this reason. Now, I myself had this experience when I was in 20s. Okay, so I was driving up a curved ramp, and then typically I maybe sometimes go a little bit over the speed limit, right? When it's a sunny day, perfect dry surface, that's no problem. But one time it was raining, so I was keeping the original. I was thinking something else. I probably didn't pay attention. So I was probably going a little bit over the speed limit, and then my car just, ran off the road, and then, yeah. So that's very dangerous. So when it's raining or when it's cold, there might be ice on the road surface. Okay, slow down. Okay, if it's a curved road. Okay, so that's something you can apply. All right. So let me see this. Yeah. Okay, that's fine. That's just an internet instant there. All right. So here we have, so again, because this is the circular motion here, so you can see again, you can follow the same procedure as we did previously. You can look at the free body diagram, and you can look at Newton's second law. So you can write out 2 equations, okay? And then in the sense, if you have other forces like spring force or friction force, then you can write out more equations. Okay, so for spring force, you can write 1 equation. For friction force, you can write another relationship. Okay, so in that sense, all right. I think we are going to stop here today. So for the lab this week, again, you guys want to bring your face shield, because I think you'll have close contact with each other when you are performing the experimental part of it. Okay, so then you can want to wear your face shield. All right, so I will stop here for today, and then see you guys later. Okay.